Okay, so now that we've at least been introduced to this different idea of programming, let's start seeing some code and how these codes are basically organized in almost every NetLogo program. So you kind of have enough to, if you were to start and write your own piece of code. So here's an example. This is actually that same piece of code from the autumn example. So from the leaves falling example, where they simulated an entire tree where the leaves were kind of the agents. Well, if I open up that code, then I end up seeing basically this structure right here, which matches the kind of structure you'll see in most NetLogo programs. At the very top, you define your breeds, which makes sense because those are like the entities of an agent-based model. So I define all the entities I need. Now in NetLogo, as I mentioned before, the way this breed works is because in the language, sometimes you refer to breeds in a plural context and sometimes in a singular. Then you need to tell NetLogo what language, like what does a plural look like? And so this is just kind of meant to be there to make things more readable. So that's why I have a breed call of leaves, which in the singular context is a leaf. You know, similar dead leaves, dead leaf, raindrops, raindrop, suns, and sun. So these are four different types of agents that otherwise I could have made them all turtles and then made all the turtles differ in their attributes, but it made more sense for them to define individual types of agents like a leaf agent. So a leaf entity. Those leaves have their own specific set of leaf attributes. So every leaf owns water level, sugar level, attachedness, chlorophyll, carotene, anthocyanin. Now notice there's a dead leaves as well. Now a dead leaf, like if I look up here, it actually doesn't say that a dead leaf has any attributes. Well, that kind of makes sense that what we would find in the code is that a live leaf, once it becomes dead, it just switches to a dead leaf, and at that point, none of these attributes matter anymore, and that's why there aren't any attributes for dead leaves. All right, now, raindrops do have their own attributes so attributes are sort of the things in which the entities can differ, the dimensions along with it. Leaves can differ in how much water they have, how much sugar they have, whether they're attached or not, et cetera, et cetera. But raindrops differ not in these properties, but in these properties. So raindrops have a location, and they give their little comment here. It's either falling in the root, so it's being sort of taken up by the tree, in the trunk, or in the leaves. So this agent-based model actually ends up representing how the water coming up through the trunk affects the health of the leaves. And so that's why they're saying that these raindrops could be located not only in the sky, but actually coming up through the tree, so in root or in trunk, or stored inside the leaves. And then each individual raindrop might have a different amount of water. And then you could imagine that as a raindrop ends up being used by a leaf, then that amount of water might decrease, or it might, once the instant a raindrop is used by a leaf, all the water might disappear immediately, but the amount of water delivered by each raindrop would be random, or lots of other things. You could imagine that this amount of water, if a raindrop is in the leaf for a certain amount of time and it hasn't been used, then maybe through transpiration, maybe through processes of heating the leaves, then you end up getting evaporation of that water and the leaf loses the water even though the raindrop is still there. And then we have global variables, and these can either be viewed as the kind of state variables that we talk about in class, or they can be thought of as accumulating statistics that we're going to sort of keep track of, but we only sort of care about at the end of the simulation. So in this particular case, it looks like they've created a bottom line global, which they say controls where the ground is. So this is effectively a parameter that they wanted to be able to change, but it wasn't kind of something they imagined changing often enough to put it on the interface. And so they just made it here so that it could be made into an interface parameter, but it's not. It sort of gets set once and forgotten about. And then they have an evaporation temperature, so the temperature at which water evaporates, and that's a similar thing where they could have put that on the interface, like as a slider, and then you could experiment with, well, as I change the evaporation temperature, then maybe I get different properties. But in their particular case, they maybe thought, well, you know what, this evaporation temperature isn't actually something that people really care about changing, but it is a parameter that we might need to calibrate in the model. And so we wanted it to be able to have an easy way to change it everywhere at once. But once we've set it, then we probably don't need to change it any after that. So that's why they've made it into this global. But in general, in NetLogo, if there's anything you want all agents to have access to, so you know all of the raindrops have access to the evaporation temperature, all of the raindrops have access to the bottom line, then you can create a global. After you define those, what the entities are and what their attributes are, then you usually define a setup procedure, which is run once, just when someone clicks that setup button, and it kind of sets up the world with its initial conditions. So just like if we're doing a hand simulation, we kind of need to know what the initial state of all of the state variables are, and even the future event list. Like we need to know, when is the sim going to end? So hitting setup sets up those initial conditions so that the rest of the sim can unroll from there. And so I won't go through their setup procedure, but it does things like it sets that bottom line parameter to just above the minimum y coordinate of the world. It sets the evaporation temperature to 30, and those are kind of set and forgot. But it does other important things, and this is usually what you see in a setup procedure, is it creates all of the agents that are, well, doesn't, I mean, you can create agents along the way, but it creates a bulk of your agents end up getting created in the setup procedure. So this is actually where the leaves get created. So I set the number of leaves in the interface, and create leaves created that number of leaves, and then of those leaves, each and every one of them run these set of commands separately and independently. So when it says set chlorophyll 50 plus random 50 draws a random number up to 50. And so basically every leaf is going to get a random chlorophyll number that might go up to 100, but might also be down to 0. So similar with water level, every leaf is going to start out with a water level that might be up to 100, but might be down to 50 because it does 75 plus random 25. So this random is actually drawn on every individual leaf, so that every leaf ends up getting potentially different values than every other leaf. But if there's anything else that doesn't have a random in it, then that will be set the same on every leaf. But it looks like they've got random on about everything here. So that sets up all of the leaves. And then for the branches, the tree, they're actually modeling as a patch. So there are patches that are located on the trunk, and there are patches that are off the trunk. And so we are looking at the side of a tree, but if you think about the world as like sort of a floor that you're running around, it's almost as if they've taken the tree and they've rotated it down so it lays on the floor, and they've cut the tree up so that some pieces of the tree are on patches that they're going to color appropriately brown and treat as a tree, whereas everything else that's not in the area that they've defined as where the tree is will end up being defined as part of the sky or part of the ground, etc. So that's there's other stuff that's going on here. I've kind of clipped it, but that's basically your setup ends up doing all of the things that you need to do before the sim, so that your sim can run and have those things guaranteed to already be in existence. So typically the setup will call a clear all at the start, and that gets rid of all other agents. And it also typically calls a reset ticks, and that I think usually happens towards the bottom of the setup, and that ends up sort of setting the clock back down to 0 and another number of other kind of housekeeping type things. Then after you set up, you see the go routine, and the go routine is the thing that ends up getting run either when you click on a button, like you could create a button called go once that calls go, or if you've created a button like a button called go that has that forever checked, it'll run this over and over again. And it's got all of the routines that you want to run to sort of make the simulation go. So if you run go, it's like thinking about a very, very small unit of time passing, moving the world along. And then when go ends, the world is a little older, And if you ran Go again, it would sort of keep making the world a little older, a little older, a little older, moving things along every time there. So in a discrete event system simulation, we jump in irregular fashion from one event to another, where the events are sort of where the system state has changed. In an agent-based model, we move things along in regular steps, not irregular steps, and it may be that nothing changes every step of the sim. So that's a very different thing, but this sort of is what defines what happens during that small unit of time. And so the end of the Go procedure will almost always have this something like tick, which will end up moving the clock forward. So you move the agents around as if they would be moved around in that amount of time, and then once they're all set in place, you move the clock forward and then return control back to the interface, which may end up causing Go to run again. And so if you look at this one, you can kind of see that, they've got these little sections here where they make the wind blow, they make the rain fall, they move the water around the ground and up the tree. They ask the sun to shine with whether it's intensity. So there are seasonal patterns, and so the intensity of the sun will change. Then they ask all of the attached leaves simultaneously to end up doing these things, which are adjusting their water, chlorophyll, etc. And then they ask all of the leaves, whether they're attached or not, to fall if necessary. And so if they're attached to the tree, they'll stay attached. And if they're currently falling, they will continue to fall. And if they just detached, they'll start to fall. And so on and so forth. And so that's kind of what's going on here. I would want to highlight that this with command, so notice that here they asked all the leaves to do something. Here they asked only the leaves with a y coordinate that is less than this bottom line. Those are the leaves that have hit the ground and are now ready to die. So now they're saying that if you're falling, the leaf is still alive. It still has nutrients and things that are in it, but it's not getting any new water because it's not connected to the tree. But at the instant that it hits the ground and goes and is at the bottom line here or less, then it turns its breed from a leaf to a dead leaf. And so those dead leaves now will not be accessed by any of these things in any future calls, because these are accessing totally different breeds. It's just flipped its breed, so it's now exiled from the leaf group. Likewise, they can also isolate leaves with a low water level, and when their water level gets sufficiently low, that's when they detach on their way to death. And so, just by setting their attachedness to 0, they're not actually detached yet, but they'll fall, and eventually the outcome of the fall is that they'll eventually hit the ground and then be dead. So that all happens in one instant of the Go. All right, so that's for a complicated example, like the leaf example. Now, let's actually then write an entire NetLogo program here and see what it does. And this does everything that I just talked about. It has, it defines attributes, it does a setup, it does a go. So if I go into my NetLogo, I can do File, New, and I've got a blank slate. So I am going to put this over here so I can see, maybe I will also get this out of full screen mode and put it over here. And then I'm going to go into my code and I'm just going to type out everything I have here. So turtles own speed. So that creates an attribute called speed that is accessible to the turtles. All right. So if we look at the next thing, to setup. So this is my routine that I will use to actually create all of the turtles. And so I'll just remind you and me that I will need to create a button that calls this, because it doesn't get called automatically. And my first thing I do is a clear all. So that is going to kill anything that's currently in the world. And then I'm going to repopulate the world. So then I create turtles. How many of them? I'm going to create 10. And I then set, each turtle runs this code separately from all the other turtles, but all the turtles you can view as running this code in parallel. So I get to set the speed of one of the turtles to a random number between 0 and 0.5. That's what this random float means. And then I'm going to set its heading to a random integer between 0 and 360. So 360 degrees. And then I'm going to set its position to a random position. So this gives me a random x coordinate and a random y coordinate. And I will then, this set xy is equivalent to me doing like set x to set x core, random x core, set y core, random y core. So I could do that over and over again, but NetLogo realizes people do that a lot, so they created a set xy where I just give them the x and the y that I want to set, and I can make them both random all in one line. And then, like I said, at the end of any setup, I do reset ticks, and that just sets the clock equal to 0. Now, I haven't set up the go yet, but let's just see if, let's just make sure I didn't screw anything up. So I'm going to go over to my interface, and I'm going to create a setup button. And I'm going to call it setup, and the commands will be setup. Now, I don't have to call it setup. I could call it set the world up. And the display name just does not matter, but the command here, that's what has to match the setup routine that I wrote in NetLogo in the code. So notice I can set the context here, and I'm, by default, I'm always in the observer context. So if I click set the world up, it ran setup, and look at that. It created 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 agents at random headings in random positions. If I were to go into my code and change this to 15, and let's say I don't want them to have a random 360, I'm going to set their heading all to 47. If I go into my interface and hit set the world up, now I've got more agents, and they're all pointing in the same direction. Okay, so you might say 47 degrees. Does this make sense that that looks like 47 degrees? Well, let's go into the observer context. So if I go down here and what I can do, so there's this interesting command center down here where I can actually communicate with the agents that are currently available without actually writing any code in the code tab. So I can actually say ask turtles set heading 0, so I can see what 0 is. And what I find there, which you might be a little surprised about, is that NetLogo 0 is actually straight up and down. So if I were to say ask all the turtles to set their heading not to 0 but 15, I find they turn slightly to the right. So for reasons that end up actually being, for historical reasons and reasons that it ends up being an okay convention that you might think that 0 should be straight to the right, 90 should be straight up and down, and 180 should be to the left. But in NetLogo, 0 is straight up and down, and 90 is to the right, and 180 is straight behind. So if I asked all these turtles to set their absolute heading to 175, they should point almost, yes, all the way behind them. So, so that's something to keep in mind is a little difference from what you might expect. But at least showing you roughly how things work here. So I got them all pointing in the same direction. I'll go back to the code, and you know what? I kind of like the random through 60, so I'll put the random through 60 back there. You say, oh, speed. Well, how do I know that that got set properly? Well, I can actually right-click on any individual turtle, and it allows me to inspect the patch the turtle's on, which shows me all the attributes of that patch and zoomed in there. It also allows me to, if I right-click on the turtle, there we go, then it tells me that this is turtle 5, so that's its ID, and if I were to then inspect that turtle, then I see all of its attributes, which include all the ones you get for free, like who equals 5 as we expect, heading is 47 as we expected, but its speed, right down here, is also, that's an attribute that I added and it shows up in this. And so while it's being run, I can actually inspect individual agents and see what things are currently set to. So its speed is set to this funny number, but that makes sense because I set all of the speeds to random numbers between, I think, 0 and 0.5. So If I were to go and inspect somebody else's speed, like this turtle, which happens to be turtle 13, I could inspect turtle 13, and I'd see its speed as something else. And then just getting used to this, this command center down here, I could actually say to a turtle, ask turtle 10 to show speed. And if I do that, then I actually get turtles. So this is another way I can inspect turtles. Or if I wanted to do something crazy, I could say ask turtles, all turtles, show speed. And it will then spit out in the command center all 15 turtle speeds. And notice the ask, this would 293. If I were to rerun that again, they come out in a different order. So ask is kind of like a for loop where I'm effectively looping through all of the turtles and having them dump out their speeds, but you can't count on the order of execution. So it's just better to conceptually to think of all of them being asked simultaneously and returning their answers simultaneously. So it's actually implemented sequentially. So if you ask a turtle to change its internal state based on the state of other turtles around it, then the state of the other turtles around it, which impact that turtle's change, may be new states or old states. So that sometimes it's important, but usually you want to try to write your code so that you don't depend on the ordering, because a lot of these things like ask don't depend on the ordering. And by the way, that actually allows them to do optimizations in the code, which makes these simulations run a little faster. So all right, we've returned the code back to the original state. I'm going to do create turtles 10, and I've already done the setup thing, so I've got my setup button. So now, so I'll go back, make sure I didn't break anything, set the world up. Good. If I did break something, like if I changed, like reset ticks J doesn't exist, if I were to hit check, it would say, oh, by the way, this doesn't work. So if I then said, well, I'm not sure what does work, maybe it's reset ticks K, and if I clicked on interface before that, it would automatically effectively run the check and bring me back here and say, no, this doesn't work. Now, if I really want to go back to the interface to see what's going on there, then I can click interface again and it'll bring me back to the interface. But the first time I click on interface, it automatically does a code check to make sure that my syntax is good here. All right. Okay. Now, I could do something advanced here. If this create turtles 10, I could call, say, population. And if I clicked on interface, it's going to yell at me because population hasn't been defined. Well, then I can click on interface again, and it'll finally let me go back to the interface. If I were to try to run this, it's not going to work because there's an error in the setup function. So that's why the code turned red here, indicating that the reason why it didn't work is that there was an error here. But I can go back into interface, and I can then create a slider called population. And notice it says global variable. And I can say the minimum is 0, as a maximum is 100. Maybe it's initially 10. So I can move that to wherever I want it to be. And then now, if I change this, drag this slider up to like 73, I get 73. If I drag the slider down to 10, then I get my 10. And every time I set, they go in random orders with random colors. So I'm going to leave that there, even though that's not what's on the slides, just to give you an example of how to modify these things. All right, so the next thing is I need to write this go routine. So I'm going to say to go, ask turtles to do something. So every turtle, when it goes, I want it to move forward. So remember, so sometimes you can use FD, that's just shorthand for forward. And forward just moves the turtle ahead by whatever a quantity I put here. Well, I'm going to put speed there. So you can think of the speed as, how is it a speed? Well, what it means is I'm going to move 0.5 patch units per tick. So if my ticks are a second, then the turtles are moving 0.5 patch units per second. If one patch is 1 meter long in my model, then this is moving at 0.5 meters per second. So I move forward speed, and then I don't want these turtles to necessarily collide with each other. So I can have a turtle check to see if there is another turtle on the patch that it has just moved on to. And I can say if any other turtles here. And so what this does is working backwards, turtles here gives me a set of all other turtles on the current patch. Other tells me all turtles, it takes this set and removes me from it. So remember, this is in a turtle context. So this is running on a turtle. So if I am a turtle and I'm running this code, then this tells me every turtle that's on the current patch, including me, and then the other turtles here tells me all of the turtles on the patch, not including me. And that might be an empty set. So what any does is it asks, is this an empty set or not? And if it's not empty, then there are other turtles there. All right? So if I found that there are other turtles at this, I might not want to be at this heading. So I just, and generally, might want to move away from those turtles. So I can say, and remember, this is just in the context of the turtle that has just encountered a patch with other turtles. I'm going to have that turtle set her heading to 180 degrees plus the heading of one of other turtles here. So again, other turtles here tells me all other turtles that are on the current patch. And grabs one of them sort of at random. And so now one of turtles here, this is just some other turtle that I've bumped into. There might have been multiple turtles on the current patch, and this is one of them that I've bumped into. The of tells me that I'm about to grab an attribute of a foreign turtle, of another agent. And so heading, I put the brackets here because that's just the syntax of, is that you have to put code inside the brackets. But this code is just simply heading. So I am grabbing the heading of this foreign turtle that I've bumped into. And so I might find that she is positioned at 45 degrees, which is often in an angle starting here and going over there. So I'm going to set my heading to be away from her. And then I can move away from her in the next step. So another thing I might do is I might set my speed to the minimum speed of all of the turtles here. So let's again unpack this from right to left. Turtles here are all the turtles on this patch. Speed of turtles here is a list of speeds of all of the turtles here. So every turtle comes back and reports her speed. And because there's multiple turtles, then all of them go into a list of speeds. And min takes the minimum of those speeds. So whenever I bump into a turtle, I slow down to the speed of the slowest turtle on the current patch, and I turn away from one of the turtles. And that's it. So the next time this go will be run, I'll move forward at my new orientation and then run this logic again. So the last thing I need to do is move the clock ahead tick. That's not necessarily, the reason you need to do that is that by default, NetLogo doesn't redraw the world unless it gets a tick. That's one of the reasons to do that. And then there's other times where you actually use the clock, and so then you actually want the clock moving ahead. So this is me manually making sure the clock's moving ahead and making sure the world is constantly moving. Let's see if I typed anything wrong. Looks like I did. This speed, apparently I meant to type set there. So it was my bad. So good thing that check was there. Now it looks like the code is good. I go to the interface, set the world up. I'd like it to go, but I don't have a go button. So I right click button and I create a go button. And I'll just make it, I'll call it go, but it could be called anything. I could call it run. Run the simulation. Now, it apparently has a problem. Oh, and that's because I swapped these. So notice when it turned red, that indicates that I screwed something up inside here. So I meant to put go here, and I meant to put the display name there. Now if I do that, then everything's fine. Now, those of you paying attention may have noticed that I didn't click forever. Well, that means that if I click on this, the world only moves one instance, one little tick ahead. And so I have to keep hitting it manually in order to get the world to run. But if I right click on this and I go to forever, then if I click 1, it latches that button down. And if I undo it, then it stops the world, but I can redo it and it'll pick up right where it left off. Now I can't see these very well, so I'm going to drag this little time thing down, and that slows them down. That's way slower than I need, so there's an intermediate speed where I can kind of see what's going on. So it looks like if anybody collided, there, I just saw a collision right there, that yellow and green. So occasionally I'll get these collisions, but it's so sparse that they're rare to witness. And so if I wanted to make sure it's working, I might crank my population up, set the world up, I'll leave it at this slow speed, I'll run the sim, and if you look closely, maybe I'll have to slow it down even farther to see this. So now I've got them running really slow. There's a bunch of these interactions, like right here, where agents are constantly bumping into each other and flipping around 180 degrees. They might even get kind of gridlocked in a cluster here because they can't quite get away from each other. Because when they turn around 100 degrees, they end up bumping into a different agent. But here's an example where two agents bump into each other and then they went off in effectively random directions. That green agent just hit the brown agent and ran off, different directions. So the code seems to be working. So that's good. And if I wanted to, I could do something like create a monitor. And I can say in the monitor, I want to know what the min speed of turtles is. And so this, I'll just say my display name is minimum turtle speed. I don't need 17 decimal places, maybe I'll put 3 decimal places. And then so if I were to put this here and click setup, then it says the min turtle speed is 004. But if I run the sim, then if you think about it, that value should probably never change because the speeds always move down based on the speeds of other turtles. But if I said, all right, well, what if I change that to maximum turtle speed? So I'll change this to a max. And then set the world up, run. It starts at 493, but once they start interacting with each other, notice that it quickly declines, or quickly goes down to 0. And I get some interesting patterns that are formed here. And it's going to slow down anymore until they all are traveling at roughly the same speed, the same slow speed. So I'll try that again. I'll set the world up, moving in random orientations, and then suddenly I get correlated motion. And it kind of makes sense that I would eventually get correlated motion because when they all are kind of moving parallel to each other, then they'll stop intersecting. And so that's kind of the point where the simulation's naturally going to settle down. So I don't know exactly where, what angle they'll agree on, but it kind of makes sense that it's possible that they're all going to come to agreement on some angles because otherwise they're just going to keep intersecting with each other. So if it's possible for them to come to agreement, then it sort of makes sense that they're probably going to come to agreement. But we'd have to run a bunch more sims over and over again to verify that that's actually the case. But just running a couple of these things, here I got not only they got correlated directions, but almost seemed like they managed to land almost on top of each other. Remember, the world is by default, it wraps around itself. So the ones that are going in this direction will come back and go to this direction. Here it actually looks like, interestingly enough, this is a very different, if I were to slow this down, this equilibrium is not them moving smoothly. This is they're actually constantly going back and forth. So the patches here, let's see, you probably can't see how big the patches are, but I could say ask patches set p color, random. So if I did set p color 0.5, then you see all the patches kind of turn gray. So if I said all the patches to set a random float between 0 and 5, then you can now see the size of the patches. And so if I were to run the simulation now, you can kind of see that what is effectively happening here is that agents that turn around end up not necessarily escaping a patch before the next go, and so they end up still being agents on their patch, and so they end up then flipping around again. So you end up getting agents like these here that keep moving away from each other, then back towards each other, and away from each other, and back towards each other. So they still are parallel, but they've sort of now moved in this like one colliding line and this other colliding line, or these two lines will never mix, but agents next to each other will never kind of move. They'll kind of constantly keep bumping into each other. So just the funny things that can come up when you run these sims that you may not have thought about, but end up making sense maybe afterwards. And that's part of the value of these simulations. All right, so let's go back to the main presentation here to wrap up. So need to go back to here. So that was a simple NetLogo example that you could build yourself. If you want to see other examples, I'd recommend taking a look at these. So in the models library, the traffic grid, that's sort of a nice one. So just to show you where that is again, to remind you, file, models library. Remember that at the instant I open a models library, I lose all my work unless I've saved it. So I'm going to go up and take a look here under social, and then look for traffic. So I could do traffic on a grid here, for example. And so this is a very basic kind of cartoon-like simulation of city traffic, but you can change things like the grid size, the number of cars, how often the stoplights change, the speed limit of the cars, and so on. So like I say, click setup, I get a different number of cars. I can hit go, and I get to watch these cars move throughout the city here. And you can see as on red lights, you get queues of cars. On green lights, cars start to flow. And I've got average wait times, average speeds, number of stopped cars. These now start to look like things that you get out of a discrete event system simulation, things that you could do some operations research on. So that's why I kind of brought that up. Other sample models here that might be interesting to read about is Hotelling's Law, or the fire model, which you'll see in the lab. You can also find online tons of other NetLogo models, not only in the modeling commons, which you can find under the file menu, but if you just go Googling, you can find things like, for example, you can find a network supply chain model, which some of you in some of your earlier classes may be familiar with these supply chain models, and you can actually run those sims inside NetLogo, or an artificial stock market where you can actually see a sim that ends up generating trajectories that look very much like a stock market. So that's all I've got for you right now for this kind of brief introduction to NetLogo. Hopefully that's enough to get you started, and I'll see you in class.